tutorial is to compute the weight, okay, of each node in the tree. Okay. Now the definition of the weight is the number of nodes in the subtree. Okay. Now if the node is a leaf node, then the weight is equals to 1. Now this is the base case. And for other internal nodes, then the weight of the node is equals to 1 plus the weight of his children. Okay, now this is the definition. Now to implement the recursive function, now there are a number of ways to write the program depending on the interface of the function. Now in this exercise, the function is defined to have a void return, so it will not return a value explicitly. Okay, so to carry out the work, and basically we will use a post-order traversal type of computation. Okay, now before we can compute the weight of the root, we need to first of all compute the weight of the two subtrees. Okay, so that's why. Okay, now in the recursive function, okay, now the first thing that we need to do is to check if the input pointer is a null pointer. Okay, now if it is not a null pointer, okay, then we compute the weight of the left child using recursion, and then we compute the weight of the right child using recursion. Okay. Now after we have already determined the weight of the two children, okay, then we can compute the weight of the root. Okay. Now to find out the weight of the root, then we make use of some local variables. So WL is the weight of the left child, and WR is the weight of the right child. Okay. Now to simplify the program organization, we try not to have multiple test cases, nested test cases, like if the left pointer is not null and right pointer is null, this kind of combinations. Okay, try to rethink a little bit. Okay, can the program be simplified slightly? Okay, so we initialize WL to 0. Now if the left child is present, okay, then we update the value of WL. Otherwise, WL will remain 0. Okay, so if the left child doesn't exist, then WL remains to have the value 0. The same for the right child, and knowing the weight of the left child and the right child, then we can compute the weight of the root. Now, knowing the weight of each node, okay, then we can write a function to determine if the tree is weight balanced or not. Okay. Now the base case is once again if the tree is empty. Okay, so an empty tree is balanced. Okay, so we return the value true. Okay. Now if the tree is not empty, okay, then once again we find out what is the weight of the left child and what is the weight of the right child. They may exist or they may not exist. Okay, so if they don't exist, then the corresponding weight will be assigned the value of 0. Okay. Now after knowing the weight of the two subtrees, okay, then whether or not the whole tree is weight balanced, okay, depends on this conjunction. Okay. Now if the difference of the weight of the left and right subtrees are no more than 1, okay, so these two comparison, okay, make sure that the weight of the left and right subtrees differ by no more than 1. Okay, if you use the function absolute, fine. Okay, but here I show you the other way to come up with the same results. Now, if the root, from the point of view of the root, is weight balanced, then the overall tree is weight balanced if the left and right subtree are also weight balanced. So this can be determined using recursion. Okay, then just taking the n operations on the 4 tests. Okay, then it will be the final results. Now the next part is to count the number of nodes by level. Okay, if you are given a given level, okay, you want to find out how many nodes are there on that level. Okay. Then there are two base cases. Okay, the first one is that if the tree is empty, then there's nothing in whatever level. Okay, that you want to find out. Okay, so you have an answer right away that is independent of the value of level. Now, if the tree is not empty, it means that you have not returned. Okay, so you have not returned, then you test if the level that you wants to find out is equal to 0. If it's 0, that means that you want to find out how many nodes at the root level. Okay, so on that level there can only be one node, so you have to answer right away. Okay. Now, if level is not 0, okay, then the number of nodes on the given level will be equals to the number of nodes in the left subtree on level minus 1 plus the number of nodes in the right subtree on level minus 1. Okay, so this is the usual way that we handle computation of this form. Now, to get the minimum value in the tree, okay. Well, first we assume that the minimum value is the value stored in the root. Okay, and then we will compare it with the minimum value in the left subtree. Okay, now if the left subtree is not empty, okay, then we find the minimum value in the left subtree. Compare it with the current mean. Okay, if it is smaller, then we update the current mean. Okay, then we do the same for the right subtree. Okay, now if the value in the right subtree is smaller, then we update mean. Okay, so after making the two comparison with the left and right subtree, then we have the answer. Okay. Now, before we start to talk about the next part, okay, that is on the hash table. Maybe let me first ask you one question. So after all those exercises, okay. So how many of you think that your programming skills has improved? So how many think that your programming skill is getting worse? No. Then what is the most useful thing that you have learned so far? Not much, right? Now actually the most important things, okay, throughout the course, when you learn how to write program, okay, you always need to go back to the very fundamentals. Okay, now when you write the programs, you try to solve a problem. Okay, so how to represent the problem, how to represent the values. Okay, so in different types of problem has different way that one may represent the information and how to interpret the data. So we come back to this concept on representation and interpretation. No matter what you are trying to write in a program, okay, it will be dealing with this aspect. And the most important things I have to say that in this throughout this course, the valuable things is not for you to memorize the example program codes in the notes. Okay, it is not quite useful. Okay, you will forget it. Okay, next week, very soon. Okay, you won't remember any of those programs. Okay. Now, but on the other hand, if you have trained yourself to be able to solve problems, then these skills, you will have it for the rest of your life. You won't forget it. Okay, so this is, you train yourself that now if you are, okay, asked to solve a problem, you have your own ability, okay, to solve that problem. Okay. Now this ability will not be forgotten. Okay. Then what is the most important aspect, okay, in problem solving? Throughout the course, okay, I emphasize a number of times is that when we write programs, basically all programs will have some kind of loops. If you don't have loops, you may use recursion. Okay? Now, recursion and looping, conceptually, they are equivalent. Okay, so you may use recursions to control the iterations. Okay, that you use it to process different items in a data set. Okay, or you may use a looping. Okay, together with the help of either a step or a queue. Okay, to control the looping. Now, the most important concept, okay, that will be valuable to you is the concept of the loop invariant. Okay. So it means that every time when you try to solve a problem, you try to think about it, okay, and then you need to be able to observe what kind of properties in that problem that you can make use of it to control the looping, to determine the results. Okay, so this is the properties that you need to identify. Without knowing these loop invariant properties, then you don't know what to do. Okay. Now, getting back to, say, today's exercise. It is the same, okay, for the problem to find out whether or not a tree is almost complete or not almost complete. Okay. Now, to solve the problem, once again, you have to go back to see what is the definition of an almost complete binary tree. The definition is given to you in the notes. Okay. Now, it says that a binary tree with n nodes and depth d is almost complete if all the nodes correspond to the nodes that are numbered from 0 to n-1 in the complete binary tree, and the numbering is based on the level order numbering. Okay, so to solve this problem, you first of all need to identify, okay, what is the properties that you can use to answer the questions. And in the program files given to you, there's a hint here that's already stated, telling you that you can solve the problem by using a level order traversal. But interestingly, that some students, when I walk around, I saw that they have already deleted 9 and then try to solve the problem using recursion. Okay. Now it's very important that in the exam, the nature of the problems, can be similar, and there are some hints given to you. You have to read the sentence carefully. Don't just delete it. Now, to solve this problem, once you see the proper invariant properties that you can use, then the solution is quite obvious. Now when you are doing a level order traversal, so if you ever see a empty node and a node that does not exist during the level order traversal, and after that you see a data node, a real node, then the tree is not almost complete. Now finding out these invariant properties, then to make use of it will be when you push the pointers into the queue, you may need to also include the null pointer. And during the iteration, when you have seen a null pointer, you need to memorize. Keep that state information. So if during the traversal you have seen a null pointer, after that you see a data node, then you know that the tree is not almost complete. If you traverse the whole tree, and get to the end, you have not encountered this situation, then it means that there's no empty node appearing before a data node, then the tree is almost complete. Now, for problem of different nature, the first thing you need to tell yourself how to solve a problem. The first thing will be, what is the loop invariant? That you can use to solve that particular problem. Now there's no universal solution for any problem. That is the loop invariant. No, sorry, in real life we don't have these things. So for different problems, you will use different invariant properties. You have to have the ability to identify these invariant properties. And I think this is the central idea of programming. Whenever you write program, you need to find out this. But there are always exceptions. Like if you are writing program to deal with the GUI, then sorry, we don't deal with loop invariant in that particular types of applications, because the GUI is more concerned about how to design the interface that is more attractive to the user, how to make the things more convenient, how to place different features. So there's not much of intrinsic symbolic computations problem behind. Now, then the last topic that I will introduce to you is about hash table. Some of you may have heard about it, some of you may have used it before. Here is to give you a more formal discussion. Now, what is the usage of the hash table? the hash table is a data structure that is used to support the search operation. Okay. Now in the basic search problem, we say that we have a data set of key value pairs. Now in computer science, whenever we use the term key, then it means that it is a unique identifier in the data set. Okay, so we don't have duplicate key. Okay. And in the search problem, then it means that if we have a data set, then if we are given a key, we search the data set for a match of the key to determine the associated value. Okay, now this is the typical searching problem. Now, how to support the search problem? Depends on how you organize the data. If you organize the data in an unordered list, then the searching time will be order n. You need to do a sequential comparisons in the list. But the time to do insert and delete will be constant. Because if you have a list, you add a new item, you can put it at the end. If it is linked list, then you can put it at the front. It doesn't matter. Front or end is the same. Now, in the search problem, in general, we are dealing with dynamic data sets. So it means that the data, in the lookup table, will not be a static table. It will change. Now, if you use an ordered list, so meaning that an array, sort the array by the key, then you can do the searching using binary search. Now, using binary search, then the searching time is order log n. It's very efficient. But the time to do insert or delete becomes order n times, because if you want to insert something into a sorted array, you need to move the data. On average, you need to move half of the data. And it is order n complexity. And if you use binary search tree to organize the data set, then the insert, delete, and the searching time are all equals to order log n. Provided you maintain the tree balance. In every after every update operation. And order log n is a good performance, but we want to be doing better than that. So one way to do it is to use a so-called a hash table. In a hash table, the average searching time is constant, and the average times to update the table, meaning that you insert or delete and add a new key value to the hash table, is also a constant value that is independent of the size of the data set. So this is the advantage of hash table. Then what is the basic idea? Now, the basic idea will be, not that complex, it's simple. Now suppose we have a data set, we denote it by the symbol sigma. Now in the data set we have n data items. So each of them is a key value pair. So we have a key and a value. And a hash table is basically an array. And we define a hash function h. And for every key value that we are going to insert into the hash table, we compute the hash value of the key. And the hash function returns a value that is between 0 to n minus 1. Now, I have updated the file a little bit. If you print it, say, a day before, then you will see 1 or 2 pages. The materials have been modified. Now the hash function will output a value between 0 to n minus 1. And then the key will be stored into the location specified by the hash value. by the hash function. Now, one simple hash function will be the mod function, okay, and we call it a division operation, okay. So basically, we do a division and take the remainder. And when we interpret the key, basically, in most systems, we just consider the key as a string of 0 and 1. So meaning that we interpret it as an unsigned value. Okay, so we have a string of 0 and 1, we interpret it as unsigned value, we do some operation on that sequence of 0 and 1 and come up with a value between 0 to n minus 1. Okay. Now for the artificial data set, the key is represented by an integer in this example. So if we define the hash function to be the key modulo by m is 11. Okay. Then 55, the record with the key equals 55 will be stored at index 0. Okay, for the key with value 35 will be stored at index number 2 and so on. Okay. Now, once we have this hash table, if you want to look up a key, then what you need to do is that you compute the hash function for the key and then go to the hash table, take out the record, make a comparison. Okay, if the key stored in the table is equals to the key of your search key, then you have found the record and you return the value. Okay, if the data item stored in the hash table at that location is not equals to your key, then depends on how you organize the table when you have collision. Before we get to that part, then first we consider a few the definition of a few terms. Now, first of all, for a given key value, the value of the hash function we call it to be the home address of the key. So it means that if you are going to go to the hash table to take out some item for comparison, then this will be the home address. Now, if the home address is empty, then you can already conclude that the key, value x that you want to look up is not contained in the data set. You don't need to do comparison with all the other keys in the table. Now, if the home bucket, we call every location in the hash table a bucket, because a bucket can be defined to store multiple items, it is allowed. Now, if the home bucket, the data record in the home bucket, is equals to your search key, then you have found the value. Now, if the key, stored in the home bucket, does not match the input, then some additional buckets may need to be inspected, depending on how you resolve collision, in the hash table. We will come to that part, a bit later. Now, first of all, we define, a parameter called the load factor of the hash table. Now the load factor lambda is defined to be n over m. Now, n is the number of records or the data items in your data set, and m is the size of your hash table. So the load factor, represents that, what is the occupancy, the percentage of occupancy of your hash table. Usually, the higher the load factor, then it is more likely that you have encountered some kind of collisions in the hash table. So it means that you have multiple keys mapped to the same bucket. Then the next term we define is the called primary clustering. Now, when we do the mapping, the key will have a certain domain. Now, for example, if you say that the key is an integer, then it's a 32-bit entity. Then the domain okay, of the key is from, say, the range of minus 2 to the power 31 to positive 2 to the power 31 minus 1. So this is the domain of the key. And M is the size of the hash table. Now, usually the size of the hash table will be much smaller than the domain of the key. Okay, now it is quite obvious because, say, imagine that, say, in US, okay, every citizen will have a so-called a social security number. The social security number has 9 digits. Okay, so the domain of the social security number is 10 to the power 10 minus 1. Okay, but the population in US is much smaller than this number. Okay, so the hash function H is actually a mapping that mapped the domain U onto, okay, the range of zeros to n minus 1. Okay, so in this case, you may already notice that if you have two, okay, arbitrary key, then there's always a non-zero chance that these two keys will be mapped to the same bucket. Okay, it is not avoidable. Okay, in general. Okay, and if you, okay, when you design your hash function, okay, if the hash function has a higher, say, the mapping of the key to the, okay, m locations in the hash table may not be a 100% uniform distribution. Okay, some buckets may have a higher chance to receive a key. Okay, so in this case, we say that the hash function have a deficiency. Okay, that is called the primary clustering. Okay, so it means that certain region in the hash table will be more likely to experience collision. Okay. And when you design the hash function, okay, we will try to avoid, okay, this okay, primary clustering effect. So when you have two keys in the data set K1 and K2, and they are mapped to the same bucket by the hash function, then we say that we have a collision. Now a hash function is said to be a perfect hash function with respect to a given data set. Okay. So in that case, for any two keys in the data set, then the output of the hash functions are not the same. Okay, so it means that the hash function will hash all the key values in the data set to distinct locations in the hash table. Then we say that we have a perfect hash function. But this so-called perfect is only for a particular data set. Okay. In principle, we cannot define a perfect hash function for any dynamic data set. Okay. As long as the domain is greater than, okay, the size of the domain is greater than the size of the table, okay, then collision is not avoidable. Now, when you have collision happen, okay, then how to resolve the collision? Okay. One simple way to resolve collision is that every bucket in the hash table is implemented as a linked list. Okay, so when you have multiple key hash to the same bucket in the hash table, then it forms a linked list. Okay, so I say some of the pages have been changed. Okay, you may repeat those pages later. Now, for this, okay, same example, if we have this, okay, set of key values, and the hash function is taking the key module by 11. Okay, then 17, okay, will be hashed to bucket number 6. Okay, and 28 is also hashed to the same bucket. Then the two keys will be organized, okay, as a linked list. Then the hash table is actually defined as an array of pointers. Okay, so if the bucket is empty, then the pointer will have a null value. If the bucket is not empty, okay, then we will have a linked list. Okay. Now this kind of collision resolution, okay, is called the separate training, and it is actually used in the the implementation of the hash table in the Java language. Okay, so it is a common approach. Okay. Now there's one disadvantage of using separate training. Okay, is that if the load factor of the hash table increase, then the average length of the linked list will also increase. Okay, so when the length of the linked list increase, then it means that the time to do a lookup will also be longer. Okay, then the performance of the system will degrade. Okay. So in Java, okay, according to the informations in the API, what they say is that the system will maintain the hash table to have a load factor no more than 75%. Okay, so when you say in a program, when you continuously add data items to the hash table, okay, if the load factor grows beyond 75%, then the system will do one thing. Okay, it will take all the data in the original hash table and relocate them to a hash table with larger size. Okay, and this is called the rehashing. Okay, so it will reorganize the data structures. Okay, such that the lookup performance will not further degrade. Okay. Now this is the basic idea. Okay, then we come back to take a look at some simple hash functions. Okay, that people may use. Now the first simple hash function is the bit extraction. Okay. Now every key value is just interpreted as a sequence of bits. Okay. So one simple way to define a hash function is that, okay, I'm going to take bit number 2, number 5, number 6, number 11 as the hash function. Okay. Then for every key, I take out those 4 bits and then form the address, and this will be the output. Okay. Now this is one approach. Okay, using bit extraction. This approach is seldom used in software implementation of a hash table, because taking the bits and then compressing it take multiple instructions. Okay, and the computation time of the hash function is relatively expensive, and the performance of the hash function may not be very good. Okay, so this idea is usually not used in software implementation. However, it may be used in hardware implementation of hash table. Okay. Then what is the difference between software and hardware? Okay. I can tell you that there's no solid boundary between software and hardware. Okay. Basically, whatever computations that you implement in software can also be implemented in hardware, vice versa. Okay. So just consider in the old days, if you want to listen to music, you have the MP3 player. Okay, inside the MP3 player is a integrated circuit. It's hardware. Okay, but today you use your mobile phone. to play songs or watch video, whatever. And inside your mobile phone is the CPU. Okay, so basically you do all the work in software. Okay, now you can do the same, okay, for the design of hash table. Now the other approach to select the hash function is called the compression or folding. Okay, so folding means that you have a long sequence of 0 and 1, you just fold it. Okay, you fold the bit sequence and then you perform an exclusive OR, okay, of the segment. Okay, after the folding, and then you reduce the bit length to a shorter length. So this kind of exclusive OR based hash function may have one disadvantage depending on what is the size of the segment that you have chosen. Okay. Now, if the size of the segment happens to be the same unit size of the input data, then the performance of your hash function will be not good. For example, if the key value is a character string, and you take 8 bits and do the folding and then take the exclusive OR. Now the consequence is that any permutation of the same set of characters, you will have the same hash value. Okay. So in that case, for a hash function of this nature, will encounter primary clustering. Okay. Certain locations in the hash table will be more likely to receive multiple keys. Now in software implementation, there are two commonly used hash function. One is division, the other one is multiplication. Okay. Now the division operation is that we use the mod function, and the value of m is chosen to be a prime number. Okay. So in general, it will give you a satisfactory performance. The other hash function is based on multiplication. Okay, now in multiplications, then you multiply your key by a constant theta, and theta, by some statistical analysis, this form of theta will give you a good performance. Okay, and after the multiplication of the theta, take the fraction, of this value, multiply by the size of your hash table and take the floor, and it will be your home address. Okay. Now there are other hash functions, based on the cryptographic algorithms. Okay, those hash functions are usually used when you have the keys defined as a variable length character strings. Okay, so it means that your key can have different length. Okay, and you want to compute a hash value that you uniformly distributes the keys to a hash table of a given size. Okay, and then in that for that kind of key value, then people have proposed different types of hash function. Now coming back to the collision resolution strategy. Okay, so collision is not avoidable. So using separate training is one way to resolve the collision. The other approach to resolve the collisions is called the open addressing approach, or using the open addressing approach, there are a number of possibilities. The simplest way is called the linear probing. Okay. This method is only used in the textbook to explain the concept, and in real life we won't use it because the performance is too poor. Okay. Now, in linear probing, what it means is that if you hash a key to the hash table and if you encounter a collision, then you will sequentially search okay, the hash table for a vacant slot to put your key there. Okay, so this is called linear probing. So you will search the hash table in a linear order once you encounter a collision. Now, here is one example. Okay, suppose this is our hash function. Okay, and okay, this diagram shows the sequence of the insert operations. Okay, so for the first time, we insert the key value 12 into the hash table. Now, using this hash function, H12 has a value of 4. Okay, since the bucket number 4 is initially empty, then we can put the key 12 into that position. Okay. Now, the next time when we try to insert the value 25, okay, now the hash value of 25 is also 4. Okay, so in that case, we say that we have a collision. Okay, we have a collision with the key that is occupying, okay, bucket number 4. Now, when we have a collision, then in the linear probing method, then the algorithm will start to search the hash table in a round robin order, okay, successively, to look for an empty slot, and then it will put the key there. So it will inspect the next slot, okay, bucket number 5, and it finds that bucket 5 is empty, then it will put, okay, the value 25 into bucket 5. Okay. Now, once you do this, it may cause collisions for the later insertion. Now, in this example, when we try to insert the value 4 and the hash value of 4 is 5. Now, bucket 5 is occupied by the value 25, and when we try to insert 4, we have a collision in bucket 5. And then the algorithm will do a sequential search, okay, for an empty slot, and then 4 is put here. Okay. Now the next time we insert 39 is not occupied, then this is put into the home address. Then if we insert 18, we have a collision, then 18 will be placed after 39. Now, so after the setup of the hash table, okay, we want to do some analysis. Okay, in the sense that when we try to look up the hash table, okay, if we have a successful search, what will be the average number of probes that we need to do? Okay, and also for the case that if we are going to look up a key that is not contained in the hash table, how many probes do we need to do? Okay, the number of probes means that the number of times you need to go to access, okay, a location in the hash table. Okay. Now, to do the analysis, okay, then for the successful search, for every key values in the hash table, okay, then we determine the number of probes. Okay. Now, if we are going to look up the value 39, then it can be found in one probe because it is stored at the home bucket. Okay, so it means that we look for 39 first, we go to the home bucket, and at the home bucket we find it. Okay, then in one probe we find the key 39. If we need to find the key 18, then we need to do 2 probes. Okay, because first we will go to the home bucket, that is home bucket 1. We make a comparison, it's not matched. Then we will continue to look for the key in a sequential manner. Okay, now in the next probe we find it in the location 2. Now for the key 12, it is stored in the home bucket and it is found in one probe. For key 25, okay, we need 2 probes. Okay, because for 25 we go to the home address 4. Okay, the key is not the same, then we compare it with the next, okay, bucket. Okay, and then we find it. Now for key number 4, we also need to do 2 probes. Okay. Then the average. The average will be the sum of the probes for all the keys divided by the number of keys. So on average, okay, we need to probe the table 1.6 times. Okay, for a successful search. Then how about for unsuccessful search? Now unsuccessful search means that you are searching a key that is not contained in the hash table. Then in the analysis, okay, we assume that the hash out value of the search key can be any one of the location in the hash table. Okay, with equal probability. Okay. Now if the home address of the key is 0, okay, and the bucket 0 is empty, so in one probe, you find out that the key is not contained in the data set. Okay, so you only need to do one probe. Okay, meaning that you inspect the hash table 1 times, then you have a conclusion. Okay. Now if you have the hash value of the key is equal to 1, then you need to probe the table for the first time. The key is not the same. Then you probe it the second time. The key is not the same. Then you probe it the third time and you encounter an empty slot. Then you conclude that the key is not in the hash table. So for home address number 1, the number of probes required is 3. Okay. Then basically you can do the same. If the home address is 2, then you probe the table 2 times. Okay, then you have the answer. If the home address is 4, then you need to probe it 4 times. 1, 2, 3, and then 4. Okay. Until you see an empty slot in the hash table, then you have the conclusion. Okay. Now you can work out the numbers, then you sum it up, divided by the number of slots in the hash table. Now summing up this column have a value of 20. Okay, and then the average number of probes required for this example is 1.82. Now you will notice that in this linear probing approach, the performance will not be very good because this method will suffer another problem. Is called the secondary clustering. Now what is the meaning of secondary clustering? Now primary clustering means that you have multiple keys hashed to the same bucket. Okay, secondary clustering means that you have adjacent cluster, okay, that collates together to form a larger cluster. Okay, that is secondary clustering, meaning that in the hash table you have 2 clusters, and the cluster grows bigger and bigger, and then 2 adjacent clusters merge to form a even larger cluster. Okay, so once you have this phenomenon, then the searching time of the hash table will degrade very quickly. Okay, so this is not a desirable practice, and because of this, linear probing is not recommended to be used. Okay, in real applications. Now, linear probing is not giving you good performance. Okay, then what other possibility can be used? Another variant of the open addressing approach for resolving collision is called the quadratic probing. Okay. Now in quadratic probing, when you have 2 keys mapped to the same hash table, instead of probing the adjacent locations in a sequential manner, the algorithm will probe the 2 adjacent slots plus or minus 1. Okay, and then it will probe plus or minus 4. the number of iterations. It will do it in a quadratic manner. So it is plus or minus 1 and then plus or minus 2 square plus or minus 3 square. Okay, so it will spread out the keys. Okay, spread out the primary cluster. Okay, so to some extent, this quadratic problem can reduce the secondary clustering to some extent. Okay, however, when the load factor of the hash table increase to some points, okay, you will have a very large cluster in the hash table. Now the other more commonly used, that is maybe really used in real life, is called the double hashing approach. Now in the double hashing approach, the program defines two hash functions. Okay, the primary hash function is used to compute the home address, okay, for a key. And the second hash function, h2, is used to compute, okay, a distance offset value. We call it the delta. Okay. Now, in case when we encounter a collision in the home bucket, then the sequence of program, okay, will be the home address plus 1 delta, and then the home address plus 2 delta, and so on. Okay, and the value of delta will be different for different key values because it is determined by the second hash function. Okay, so in that sense, this will also try to reduce the primary clustering. Okay, meaning that the primary cluster, all the keys that have collision in a bucket, will be spread around into different places in the the hash table. Now, so far, is there any questions? Okay. If no questions, then here is one example on using double hashing, okay, to set up the hash table. Now, the primary hash function is the same as the previous example, okay, but the second hash function, okay, is 1 plus x modulo 5. Now, the output of the second hash function cannot be 0. Okay, because it is used to determine the distance from the home bucket. Okay, if it can produce a value 0, then you will have an infinite loop in your program. Now, the home address of the key 12 is 4, so 12 is stored here, and the home address for the key 25 is 4, then we have a collision. Now, after having the collisions, we compute the delta using the second hash function, and in this case the delta is 1. Okay, then it will probe the next slot in the hash table. Then 25 will be stored here. Okay. Now then for the key number 4. Now key number 4 will have a collision with key 25. Okay, because 25 occupy his home address. But then, H2 of 4, will be 5. Okay, here I missed out this. H2 of 4 is also 5. Okay, so the key number 4 will be the program will try to check the location 5 plus 5. Okay, it will check location 10, and location 10 is empty, then the key 4 will be stored at index 10. Okay, now you can see that in this case, compared to the linear probing. Now, in the linear probing, we have a larger cluster formed in this region. Okay, 3 consecutive locations are occupied. Now, the key 4 is changed, okay, to be stored at index 10. Okay, so the size of the cluster is actually reduced. And then for 39, okay, and now for the key 18, okay. Now for the key number 18, first it has a collision with 39 at the home bucket number 1. And the value of H2 of 18 is 4. That means that the program will try to put the key 18 at bucket 5. And now it is already occupied. So we have, okay, collision again. We will then try, okay, bucket number 9. Okay, because the distance is 4, okay, from the previous bucket. Okay, so 18 will be stored in this position. Okay. Now this will be the setup of the hash table after the 5 key values are stored into the table using the double hashing approach. Now once again we want to find out the performance, okay, of the hash table, okay, in terms of, say, for successful search, what is the average number of probes, and for unsuccessful search, what is the number of probes. Now for the successful search, it is usually easier to find out the okay, average number of probes because you only need to consider the individual keys. Okay. Now for key 39, it is stored in the home bucket, then it can be located in 1 probes. Okay. Now then for key number 12, okay, key number 12 is also stored in the home bucket, and it is located in 1 probes. Then for number 25, okay, now number 25, the home bucket is 4, okay, and then we will follow the same sequence, okay, based on the delta value. Okay, so it will be probe, the second probe will find, okay, the value 25. Okay. Then for the key number 4, okay, it is also found in 2 probes. Now, but for key number 18, first we will probe, okay, the index 1, okay, bucket 1, and then we will probe bucket 5, and finally find it at bucket 9. So we will find it in 3 probes, okay, for key number 18. Okay, then the average number of probes in this example for a successful search is 9/5, is 1.8. Now, then for unsuccessful search. Now for unsuccessful search, the analysis is more tedious. If you are probing an empty bucket, then you have to answer in 1 probe. Because every time you see the empty bucket, you have a conclusion that the key is not in the hash table. However, if you are probing a bucket that is occupied, then what will be the average number of probes required to eventually the program has the conclusion that the key you are searching is not there. Now then it depends on the output, the domain of the second hash function. Now in this case, the output of the second hash function can have the value from 1 to 5. Okay. Then for every possible value of the H2, that is 1, 2, 3, 4, 5. For each of the 5 cases, you follow the search path in the hash table. Then you determine how many probes you need okay, to make a conclusion. Okay. Now, if the home bucket is 39 and delta is 1, then in 2 probes you have the answer. If delta is 2, you also need 2 probes to find an answer. If delta is 3, then 1 probe, 2 probes, and 3 probes, then you have an answer. Because, okay, when you are following the search path, okay, you need to inspect the hash table 3 times. Okay, so you will work out for every possible value of the output of H2. Okay, then you have the average case, okay, for this particular bucket. Okay, so after all the detailed analysis, okay, this will be the average. Okay. Now after this discussion, you may think that now hash table may not be very good. Okay. Once you have the collisions, you have the clustering, then the performance is no longer okay what we say at the beginning. That gives you constant time performance. Okay. Now, in reality, okay, separate training is commonly used. Okay, because the concept is the concept is simple. Okay, and the performance in general is quite good. Okay. Now, I will introduce you one more method, okay, for organizing the hash table. That will give you a relatively good performance for lookup. Okay, and this method is called cocoon hash. Now this method is invented in 2003, okay, by 2 researchers. And this method is actually a dynamic perfect hash table. Okay, so dynamic means that the data set can change. Perfect hash means that, okay, the time to search the table is guaranteed to be a constant value. Okay, at most 2 probes, then you have the answer. Okay, if the key is in the hash table or it is not in the hash table. Okay. However, the insert operation may take longer time. The delete operation is constant time. Okay. Now the idea of cocoon hash, okay, actually I think it is quite interesting. Okay, is that the physical table, okay, the data structure actually contains 2 hash tables, T1 and T2. T1 and T2 can have the same size or different size. Okay, but you will have 2 different hash functions, H1 and H2. The 2 hash functions cannot be the same. It must be different. Okay, and the operation of the hash table is that for a key, okay, if it is to be placed into the hash table, it can be either put into T1 at the bucket H1X, or it can be placed at the table T2 at the address H2X. Okay, so it is either one of the 2 locations. Okay, and if you want to insert a key to the hash table, okay, then the process will be visualized in this diagram. Okay. Now, if you want to add the value x to the hash table, now the logical hash table is a pair of table T1 and T2. Okay, now H1X, okay, suppose map to this location occupied by Y, and H2X map to a location in T2. Okay, we don't know whether it is occupied or not. Now, the operations of the insert function is like this. It will first try to store X into T1. If the bucket is occupied, then the program, okay, will knock out the value Y and put X into the location T1. And Y, when it is locked out, okay, the program will try to store it into T2 using the hash function of T2. Okay, now if the home address of Y in T2 is occupied, then it will lock out the key, okay, in T2. Okay, so Y will occupy, okay, the slot, and the key Z is locked out. And then it will use the first hash functions to see if the home bucket for this value is empty. Now, if it is empty, then Z will be stored here, and the insertion finish, stop. Okay? So by organizing, okay, the keys in the two tables in this way, okay, so when you do a search, you go to check the bucket in T1. If it matches, you have the answer. If it doesn't match, you go to check the bucket in T2. If it match or no match, you have the answer. Okay, so there's no collision resolution strategy involved. Now, but there's one potential problem. Okay, in the insertion process, if you have a sequence of keys, okay, that form a loop, then your insertion will fail. Okay, now this is one such example. Okay, now suppose the setup of the two tables, okay, for the corresponding slots are shown, and the arrows represent the mapping defined by the hash function. Okay, now to insert X into the hash table, we follow H1. Now this slot is occupied, then Y will be locked out. Okay, so by putting X in this position, Y move to T2, and then it will lock out the key Z, and in turn it will lock out the key U. Okay, and U will go to T2 and lock out V. And if V is supposed to be mapped to the same location of X in T1, then X will be locked out again. Then it will try to put into X in T2. Okay, now T will lock out S, and S lock out X again. Now X is, okay, cannot be stored. Okay, so in this case, we find that we form a loop. Okay. Now the insert function, okay, the pseudocode will be like this. Okay. Once again, I have to tell students that this pseudocode has been revised. Okay, because the first version is based on the one used by the authors. Okay, and the looping is controlled by a threshold value, but here I change it by the detection that the original key has been locked out from T2 again. Then you know that you form a loop. Okay. Now the insertion process, okay, you will like this. First of all, you try to look up the key. If the key can be found, okay, then the insertion will be ignored. We do not allow duplication. Okay. Now, if it is not initially contained in the hash table, okay, then we save the original key value, okay, for the detection of forming a loop. okay, to be used later. Okay. Then we will use a do while loop, okay, to perform the instruction, because we will at least go through the loop one time. Okay. First, we try to put